looking last week at bubble sort. So remember that bubble sort is an algorithm that tries to sort something by taking, also this is fine, by taking a list of sorted values, like represented like we have in the visual thing here, picking an element, and then having it move until it finds something that it is in position with. So if we have a really big element in the front, perhaps do it this way, big guy here. The idea of bubble sort is it's a sorting algorithm that says, how do we get this guy right here to a position over where he belongs at the end of the array? To do that, we look at the rightmost neighbor, and if this guy should be to the right of this one, then we go ahead and swap them. And we end up with an array that first draws this one here, and then draws this giant guy right next to it. Then we keep repeating this process over and over again, making these swaps, until eventually the biggest element bubbles all the way over to the right, and we end up with a sorted array. This happens in quadratic time because we have two nested loops. We have to get this element over to the end. That takes linear time. And we have to do that for every element. So we have to do a linear time thing inside a linear time thing, which gives us that quadratic structure, having a for loop nested inside of a for loop. And we saw some of the runtime examples that when we built it out our own way, it took us 8 seconds to sort something with 1,000 elements. But Swift has a faster way that we'll get to still a little bit later that can do it in 0.02 seconds. So quadratic algorithms are bad, but interesting. And they're interesting because they have a much more intelligible approach to how to be solving something, and people came up with them first. So that was what we saw last time with bubble sort. Let's see if I can bring up that sounds of sorting thing. I'll give up on the audio part for now, but at least to get the video up. So the idea with, let's see, sounds of silence. Listen to some Simon Garfunkel. Sounds of sorting. Do not restore pages. Don't want any part of that. Okay, so the idea with our bubble sort is that it moved like this. Not gonna have the notes in it, but makes some really fast swaps, gets all these big elements bubbling up. This one's inverting it, so it's taking the small elements and bubbling them down to the end. It's called bubble sort because you see all of the elements bubbling down to what you want their end position to be like. So this is the idea of what a bubble sort algorithm is doing. What we're going to be looking at today is another bad sorting algorithm, a quadratic one that's a for loop and a for loop. And we're going to be doing it two ways. The first way we're going to be doing it is a way that's a little bit simpler, but takes a little more space. The second way looks like this, which I'll put up right here. And this one is called InsertionSort. Let me put it back in descending order, re-randomize it, and take a look at what insertion looks like at lower speed. So the idea with InsertionSort is we pick each of the elements, and as we find it, we maintain a sorted section over to the left and an unsorted one over to the right. When we find a new element, we want to insert it at the spot that it should go at in this sorted portion. So we iterate down our list, then once we hit something that in our unsorted portion, we then go back the way that we came from until we find the place that it belongs. It's called InsertionSort because as we find new elements, we are inserting them back in the place where they belong in the previous array. So that's the basic picture of InsertionSort. Let me play it going the other way, why not? The basic idea is we iterate through, we find elements, and then we insert them at the position that we want them to be at. So doing it this way is called doing it in place. When you hear that in terms of a sorting algorithm, that means that you get an array in as input, you don't make any new arrays or any new structures, you just mess around with the internals of that one array, and then you hand it back. In-place algorithms happen without allocating any additional space. Just like we have time complexity that we've talked about a little bit, you also have space complexity. Space complexity means how much more memory do I need to allocate in order to be solving this problem? If you are using insertion sort as it's modeled here, you do not need to allocate any new space for it. You maybe make a couple variables, but that's it. If you have an array with 11 billion elements in it, doesn't matter. You just look at them and you can all shuffle them around until they're where they're supposed to be. That's called an in-place sorting algorithm, and it works in constant space, all one space. They're a little bit trickier to write, so we're going to do this first using a not in-place sorting algorithm for insertion sort that works instead by doing something you've done a lot. You make a copy of your array, and you mess around with the copy, and then you return the copy. We're doing this first because it's a little bit easier to understand how we might be building something with the same conceptual idea, and also to motivate why might it be a good idea to do something in place? Why might people be interested in that? What this looks like in Swift is when you, put this in presentation mode, but after that, when you are sorting something, these are two good keywords to know about, is let's say that you have some array, 1, 2, 3, like so. So you know that if you try to sort something, or do a lot of things to arrays, there are two different things that come up here, sort and sorted. What's the difference between these two methods? Yeah, I go for it. Exactly. So, and if you look at the terminology that they use, which I didn't know before I looked at this, but I'm glad it uses the same terminology. It says here that it sorts the collection in place, right? So what that means is it's not allocating anything new to be sorting that array. It's doing it only with that existing array. Dot sorted says it returns the elements of the sequence sorted. We're making a whole new collection and then giving it back to you, or sequence in this case. As a fun side note, the reason why sort and sorted appear for arrays and strings and dictionaries and whatever is because they all conform to collection and to sequence. So those are protocol methods that someone built out on sequence, and array conforms to sequence, and that's why it knows how to sort things. It's kind of fun. What that means practically is if you make something that's a let and then you try to sort it, it should give you an error because you're not allowed to mess around with immutable values. So that's a little bit of prefacing on how might this be actually useful in development. You should probably know the difference between sort and sorted and understand that one of them does it in place and one of them does it by making a copy and then giving you the copy. Okay, so that's a basic sort versus sorted distinction. Let's go ahead, and the first thing that we're going to build is a not in place insertion sort. So we could do this, yeah, we'll just call this insertion sorted. We'll take some array as input. We're going to have it be an array of some generic type t. And we're going to have an is sorted that tells us whether or not the array, two values that are given into the array are sorted. This should return an array because we're going to build some new array and get it back. So insertion sorted is going to take an array in, take some sort of closure that tells us what does it mean for two numbers to be sorted really. We saw that before. We could just assume that everything should be smallest to greatest, or greatest to smallest. But we might get some really weird t in for our types. Like if we have an array of person objects, the user might want greater than to mean a user ID number, or maybe an age, or maybe an address or zip code, or maybe first name alphabetically. There's a lot of ways you might want to sort certain objects. So building our method with these generic types allows users of our API to indicate what they mean by two things being sorted. And that's the same thing that Swift sort has built into it. So the first thing we're going to do is we're going to make a copy of our array. Because this isn't in place, we can go ahead and do that. The super fancy name for what we're doing is called variable shadowing, which sounds like it's sort of some like evil secret society or something. but it really just means we're creating a variable that shadows an original one that we're allowed to manipulate and translate around. So we've got our variable here, and what we want to do, and we're modifying the algorithm a little bit to make it easier for our in-place sort, for our not in-place sort, is we're going to get an array of unsorted stuff. 3, 2, 9, 4, I always use 9 and 4. 9, 4, 7. There's a lot of ways we could try to build and recreate this. We're going to stick with one of the most simple ways to understand what insertion sort is doing. What we're going to do is build, and this is maybe the first sort you would come up with if someone just asked you to write a sorting algorithm. We're going to build an empty array here. We're going to iterate through the array. And when we find an element, we're going to find out where it should go in this new array of sorted stuff and put it there. So we see a 3, our array is empty, we put a 3 inside. Now we see a 2, we look to see, we iterate over on this array here until we find something that's bigger than us, and then we put ourselves right before. Then we see a 9, we iterate through until we find something that's bigger than us. We don't, we get to the end and we put it there. We see a 4, we iterate through until we find something bigger, we find a 3, or we find a 9 rather, and so we put our 4 there, and then we do the last thing for the 7. At the end of the process, we will have built a perfectly functional sorted collection that has all of the elements from the first, but now in sorted order. So this is kind of the worst of sorting algorithms in the sense that it takes quadratic time, and we have to make a whole new array to do the work for us. Why is it worth doing? It's good to get some familiarity with how to build things that are functional, and this is a pretty good introduction to like, what does it mean to be inserting something? What does that process look like? So let's go ahead and just code it up. Something that is good to practice, this whole process of let's come up with an idea, let's figure out how this algorithm works, let's code it, is your bread and butter of algorithm interviews. Ideally, even if you've never seen this before, if someone explains a process to you about how we want to be going through it, you should get to a point where you feel comfortable translating that into code. The easiest way to do that is when you're writing code, start thinking about it in terms of what you want it to be doing and less in the keywords about what you're using. So for example, like when I say something here like, I'm going to iterate over this array, try to think of that when you're writing for I in R, like for element in R. Try not to think for element in R. Try to think for each element in this array, I'll do this. And the more you can be reasoning about the code that you're writing in ways that you could be explaining it, the better position you'll be in an interview where you will need to be explaining code that you have written, and the better developers you'll be in general. So, we've made our copy of this array here, which we might actually need to do, that's fine. We now need to make our empty array, so we'll call this sorted array, and that's going to represent our sorted collection of stuff, and that's going to be an empty array of whatever this generic T is. Brief note on this, just from what I've seen in some people's. I've seen a lot of people that might name this on line 10 something like empty R, because they're like, well, I'm making an empty array. You should always name things with their function, not what they happen to be when you make them. This array is empty right now, but what it represents is the sorted array that we have. So empty R is a bad name for the array on line 10, because it's not going to be empty if our algorithm does what it's supposed to. It's going to fill up with stuff. What's the stuff it's going to fill up with? Oh, it's going to be the sorted array is what this represents. So times to be picky about naming are absolutely when you're doing algorithm questions. It's really good to be thinking about what have I named things and what does this represent? What information is this going to be warehousing? What's going to be stored here? And how can I be illustrating that to someone looking at my code? Okay, so now we have our sorted array. What we need now, we're going to build this actually separately since we'll make it a little bit cleaner. We want an algorithm that takes in an array and an element and puts that element at the right spot in a sorted array. So we want to build an algorithm here that inserts an element into a sorted array. And the element should be of type T. So our function here is going to be a little helper function to do the work of this step of the process. We could do it all in the same function. I messed around with that a little bit first. It looks a little bit messier, so this will just separate it out and make it a little bit cleaner. So now, as we insert elements into the sorted array, we get back a new array, which represents the array combined with this new element that we have here. So what we're going to do is, we don't know what the implementation of this is yet, but if we iterate over the elements in this array, and then we reassign the sorted array to be whatever we get when we insert this element into this sorted array, and then we return the sorted array, then we'll have our solution. So this is one example of how modularizing your code can make things a little bit more readable. And here we get a warning, and this is fine practice. The warning's telling us that sorted array, sorted R, is a let instead of a var. Now we can go ahead and change it. It's actually not bad practice to make everything lets and then just change them when you actually need to mutate them, unless you know for sure you want to be mutating them. So now our insertion sorted reads pretty cleanly. What are we doing? We're going to be taking, and we actually see, we don't actually need our shadowing here since we didn't even end up mutating it. So we're going to make a sorted array. Then for every element in the original array, we're going to insert it inside the sorted array, reassign that new thing to our sorted array, and then return the sorted array that we built. So hopefully this part makes sense. So what we're going to look at now is, how do we solve this algorithm question? Given an element and a sorted array, return a new array that has the same elements, except also the new element still sorted. That's the question that our line 16 function wants us to be solving. So the example that we had here, let's say before we add the 7, the inputs to this function are this sorted array and the value 7, and the output should be a single array, 2, 3, 4, 7, 9. So that's the input to this function. This is the output to this function. It's always good to be breaking down the work that you're doing as much as possible into these modularized components, if it's something that you can do. So what is the process for translating these inputs into this output? If we know that this input is sorted, then what we can do is march forward one element at a time. And once we get to an element that's bigger than we are, insert this element at the place where it needs to go. So we're going to march through. Once we get to the place where we need, once we find something that's bigger by whatever this closure is, so we're going to need to know what it means for two things to be sorted. So I'm going to add that here. By is sorted. We'll need to toss our closure on over, because we don't know what it means for one thing to be bigger than some other thing. And now we do. It means that it returns true when it's passed into this closure. So we're going to start here, march forwards, and once we find something that by this closure is bigger than us, then we're in position. Right, so we take this 7 here. 2 is not bigger than 7. We keep moving. 3 is not bigger than 7. 4 is not bigger than 7. But 9 is bigger than 7. So we want to put ourselves right before that 9. So let's code that up. So we're going to go ahead and this time we'll make our copy of sorted array here. Our sorted R is equal to sorted R. We're then going to iterate over our sorted array here for element in sorted array. And as we iterate over our sorted array, we're going to check to see whether or not this element, perhaps I should give a better name, perhaps new element, whether our new element is sorted with the thing right after it. So we'll check that right here. If is sorted, which is this closure right here, element and new element. Is that the right way? Think about that for 1 second. So if it's true that new element and element, did I reverse that? If it's true that new element belongs before the element, then we want to go ahead and insert that at the right index. And we can find that index by grabbing the indices as we're iterating through with that dot enumerated call. Lots of good stuff for index and sorted r dot enumerated. Okay, so now we know the index we should be at is at this index right here. That's where we want to be inserting our new thing. And it's at that index because before index 0, 1, 2, 3 was 9, and we're saying we actually want index 3 to be 7 instead, and index 9 will now be, value 9 will now be index 4. So we're going to take this sorted array, and we're going to insert new element at index. Then we're going to return the sorted array. Because we don't, once we found where it belongs and put it in, we're done. We don't need to do anything else. Helpfully, our function xcode is now telling us, well, you didn't really finish yet, right? What happens if I get through the for loop and I never return? Well, that's a great question, xcode. What we want to be doing is if we get to the end and we didn't find anything that was bigger than it, then that means it's the biggest. So we put it at the end. So we can go ahead and add our element. So sorted r dot append new element. And then we can return our sorted array. So what we've done here is we've built out a couple-step approach to an insertion sort. Our insertion sorted thing is pretty simple. We're just iterating through our whole array and then doing something with every element in it. And what we're doing is we're grabbing its value and finding where it belongs inside this new thing. Let's do a quick check to find any bugs we might have left around. So if we make an array of, let's say, we could use that actual one we built, right? 3, 2, 9, 4, 7. And then print insertion, and that's Windows NT operating system. It's a good thing to print. R by less than, and then see what it does. Redeclaration of R. Oh, I already have an R. No more. Okay. Then we can see whether or not this delivers our sorted array. We see that it does. We could run it through a bunch more cases, but we'll rest in the assurance that we have built something that's going to be sorting this array here. So this is a not in place insertion sort that's adding the stuff that we want. Now, there's a couple things that we want to be improving on this. First, we would love to make something that doesn't actually require using more memory. We'd use a bunch more new memory in this one, and that could get expensive. But if you're just using ints, ints are really small. You can make as many ints as you want, so it's not going to use that much memory. But like, imagine that you were sorting things like media files that were like megabytes each or something for some reason. If you were storing, like you've done some work with storing and persisting images, right? If you have some really large, high-definition images, and you're storing them in like file manager somewhere, and then you get them back, and then you want to sort them by a timestamp metadata, which is a very reasonable thing you might want to do, and your algorithm makes a copy of all of them, that's really expensive. You might end up allocating a bunch more memory, and if you allocate too much memory, iOS gets mad at you and kills your application. And that's a bad user experience. That's probably something that happens, like if you're just using an app doing something, and then you just are looking at the home screen and just like broke, it's probably because either someone force unwrapped something, or it was allocating too much memory and it just got killed. There's a lot of reasons why it might get killed. This is certainly one of them. So it's good to understand what's happening behind the scenes. How is Apple making sure that it's not allocating too much memory when you have a really big array that you want to be sorting? Okay, the neat keyword for that is going to be in-out. Have you seen that keyword anywhere yet? Let's go over it here. So we're going to make our insertion sort using that same terminology. We're going to take some array, also generic t. We're going to take some is sorted closure, which is going to take in some t, return a bool. And this one's going to return nothing, because it's going to actually mutate this array. It's going to change this array, really. But how do we do that? Every time, if you just try to change R around right now, and you're like, well, I want to change R. I want it to be something else. Let me say R is now equal to this other thing. It's going to give you an error on 27, so you can't do that. It's a let constant. You're not allowed to do that. So how do you get around that? Usually, structs are what we call passed by value, which means anytime you use another function somewhere else, you copy all the things it did anyways, and then you give them that copy. So it doesn't let you mess around with it, because it knows you don't really have this array. But we can be cleverer than it. Well, not really, because they built it in. But the keyword in-out means the same array of generic t that you give into me is the same one I'll give back to you. This really ends up changing the array that you have in memory. It is rare, like most things we do here, but it is rare that you would want to write an in-out function outside the world of algorithm solving. If you're just writing a regular iOS app, you're building a table view, it's very rare that you would A, be working with structs in the first place, if it's any sort of UI kit object, but B, that this wouldn't be better served by making a class, or making some sort of protocol, or or just passing by value. But behind the scenes, in-out things are used sometimes to be making sure that you don't need to be allocating more space. And you can tap into those keywords. So we're going to want our function to be in-out so that we can be actually mutating this original thing that we worked through. Okay, let's take another look at this algorithm to try to understand what is the in-place one doing for how to be sorting it. So this is our insertion sort. So what we're doing is we're maintaining, keep this frame if you're looking at it, a left side of sorted stuff and a right side of unsorted stuff. And as we go through, we'll be making the sorted stuff area bigger, the unsorted area stuff smaller. So as we find new elements, we keep iterating forwards, then we go backwards until we find where this element should belong. So we go forwards to find our new element, and then we keep iterating backwards to find the right position for this element. And this one here is building in greatest to smallest. You can build it in all sorts of different ways. So we have the vanguard is always going to be either the minimum or the maximum. That is going to be kind of the boundary line between your sorted stuff and your unsorted stuff. You'll pick up a new friend and then shove them backwards until they find their correct position in line. So this one's a little bit trickier as an algorithm. Might look at my notes for this. But it's a very clever solution to it, and it does work in place. Let's see how I began before. These are both insertion sort. The top one I would call not in place, linear time insertion sort. That's kind of not optimal. The one that we just saw is also insertion sort, but it's a more efficient version. So let me take a quick scan here. Get rid of that. Okay, looks good. Very clever. All right, let's go for it. So, good thing I did this before, right? Okay, so what we're going to do is iterate over our array, pick the same array to start with if we like, except instead of taking the element and putting in some new thing, this array that we kept here is secretly inside this array. Is kind of how you should be conceptualizing it. We start off and this has it's not actually a thing in code, but a secret boundary of our sorted stuff that doesn't have anything in it. Or it has the first element in it. This bit represents the stuff that we sorted so far. Then we expand out our sphere into the next element, and we say, hey, keep swapping until you get to a position where you and your neighbor are now in a sorted position. So after that first step, we'll end up with a 2 and a 3 being our sorted vanguard, and then 9, 4, and 7 being unsorted. Then we need to repeat the same thing with the 9, so we expand our scope out to include the 9, bubble it back until it's already sorted. That's the beginning here. So 2, 3, and 9 mark our sorted part, 4 and 7 are unsorted. It's not actually a subarray we're keeping, it's just a way of bracketing out the values we have. Then we'll do the same thing with our 4. We'll expand out so that our scope includes this thing here. And then we'll bubble it back until it finds where it's supposed to be. And then do the same thing with the 7. It's a neat process. The logic behind it can be a little bit tricky. So what we want to do first is iterate through every index from 1 to the end of our array. We're starting at 1 because this value is already sorted relative to itself. We don't need to do anything to sort this 3 here. We can start at 0. We'll just look at this 3 and then leave it. For each of these elements, can I make something up there? No. Okay, we're going to make a copy of our first index and call that index 2. So what we're doing here is we're saying we're going to freeze whatever position we're at. So let's say index 1 is going to be, like if we're at this 9 right now, index 1 is going to be 2. And we're going to make some new variable index 2 that's going to start here and then move backwards until it finds the place it's supposed to be at.
You say it again?
Yeah, it's a little bit tricky. So what we're going to do is we're going to take this index 2. It's going to start here with a value of, in this case, 2. And then we're going to say, at each step of the process, as long as index 2 is greater than 0, right? So we don't want to go out of bounds. And it's not the case that this is already where it belongs. Then we're going to keep shuffling it backwards. A little bit of a tortured logical train, but that's a basic idea. So we're at this 4, let's say, at index 0, 1, 2, 3. And we say, as long as this index here, which we talked about index 2, is greater than 0, and it's not true that it's already where it belongs, swap these 2 elements and bubble it backwards. Well, it's very clever to come up with this. I certainly could do. So we need to write that condition, right? We want to bubble everything downwards such that it either ends up at the beginning, if let's say we have like a 1 at the end here, 1 is never going to be sorted with its leftmost neighbor. It's just going to find the beginning. Other elements eventually are going to be sorted with their leftmost neighbor. So we're going to bubble them down until they end up in the range. Okay, so we need a way of tracking. Yeah, okay, so we're going to be comparing to our leftmost neighbor for this. So while our condition for this, while our index 2 is not equal to 0, or greater than 0, I suppose you could say is a little more clear. That's the same thing. And it's not the case that the array at index 2 minus 1 and the array at index 2 are already sorted. Do the following. This is a doozy of a while statement right here. So what we're doing is we're saying, while the index is greater than 0, that would make sense. We're good with that. And it's not the case that if I look at this element here and this element here, I conclude that from the closure, they're already in order. do the following. So when do we break out of this loop? One of two cases. Either our index 2 is equal to 0, or, in which case we don't need to do anything since we've already gotten to the beginning and we bubble back and there's nothing left. Or it is the case that our element at index 2 minus 1 and our element at index 2 are already sorted. Again, a little bit tortured, but the way of exiting this loop is either we're at the beginning or we've already sorted the thing that we're trying to sort. You can spend a little bit on just a sentence here, that's okay.
The thing we're trying to sort is at the beginning.
Mm-hmm.
Conceptually, is it where it's supposed to be at that moment in time?
Yeah, so the only way to get back to 0, that's what you're saying, right, is if it starts off, either we start at 0, but let's say we start off at 1 billion or whatever, index 300. If we end up at 0, that means it was never true that it was sorted relative to its left neighbor, right? So the only place for it to be is at the beginning. So if you take, let's say you take 0 in an array that has numbers 1 through 99, and the 0 is like at the end, you're going to end that loop when the index 2 is 0, because you've compared 0 to its leftmost neighbor, and you're like, these still aren't sorted, and then you swap them. And then you keep repeating that process by making index 2 smaller, and keep swapping. So what does that look like? Finally, we've got swap at, and we'll take a look at some iterations of this. You noted here, you see this weird like ampersand thing? Why do we think we have that? What's weird about swap? It's an interesting one. So swap takes in two things, right? And actually swaps their values, like really swaps them. Even if they're structs, it's taking not the values, but the references. And we've just seen here, a key word for doing that is in-out. So if we type swap in here, it's really exchanging them, and the ampersand is what you use when you're dealing with in-out stuff. So we'll see that later. It's just kind of a fun preview here. We can also use r.swapAt to say that we're going to take this array here, and we're going to swap at index 2 minus 1 and index 2. Then we're going to take our index 2, and we're going to decrement it. Real doozy here. So this might be the densest like 3 lines of code I think we've seen yet. What we're doing here is we're picking our index 2, starting at wherever we are in our iteration so far. Then, as long as it's bigger than 0, and as long as it's not true that the thing is already sorted, we're swapping it with its left neighbor. Then we're moving an arrow backwards and repeating this process until we either end up at the beginning or it's already sorted. Once we've done all that, that's actually it, right? I guess we could, why is this return array? Yes, once we've done that, we're done. We've sorted this array. Seems a little bit weird. Let's put some print statements and actually like look at what the heck is happening when we try to run this algorithm. So every time we run this here, let's have it tell us what is the value of index 1. Index 1 is equal to, this is like, this is probably one of my favorite tricks when you're ever working on an algorithm, is just have your algorithm tell you what it's doing. It makes life a lot simpler. If we want to see what the heck does this look like when we run it, you can do this on pen and paper. You can also do it by having your algorithm just tell you what the different values are. So here we can go ahead and every time we do something, we make a swap, we're going to print what this array looks like. Then we're going to build our random element array. We're going to do this using that same old trick we saw before. Let's go, the numbers from 0 up to 1,000. We'll take that range and then we'll map it. So our map is going to say just take a random element in int.random in bunch of random numbers. Let's make it a little bit smaller. So then we'll go ahead and take this random element array, and we'll try to call our insertion sort on it. Make this a var first, because we're going to be messing around with it. So we're going to call InsertionSort. That's our in-out here, which is on this random element r. And our sort is just going to be less than. Then this will do a bunch of printing for us, so we don't need to say anything else. Let's rumble. Okay. Hopefully this doesn't loop forever, but we'll see what happens. Welcome so far. Keep in mind, this is still a quadratic algorithm, which means we didn't loop forever, but we only had 100 elements, and it took us 24,000 times, or 2,400 times to go through it. This is still not an efficient sorting algorithm. It's still a quadratic algorithm because we've got a for loop, and we've got a nested for loop inside that for loop. And whenever you have that nested structure, you end up having these really, really high numbers, or not that high numbers of how many times we're going through our first loop. So this is a really inefficient algorithm, but it is a little bit easier to understand conceptually what it's doing. So what does this look like? Good Lord, there are a lot of elements here. That's way too many elements. All right, let's try 10. I can't think that quickly. Okay, might be easier to look at with 10 elements. There we go. So with 10 elements, we see that our array looks something like this. And as we look at subsequent lines, index is kind of distracting. So we look at 1, we look at 2, those are already where they're supposed to be, right? 148 is at the beginning. 623 is greater than 148, so it's where it's supposed to be. Then we look at our next thing here, which is this 246, where the index 1 is 3, and we say it's not in the right spot. We swap it back 1, and now it is in the right spot. We're then looking at 4, which is this 424 thing. Actually, is that right? 0, 1, 2, 3, 4. Interesting. Then we look at this 882 thing we ended. Did we actually sort this correctly? We did sort this correctly. No, actually, we didn't. Fun, we got a bug here. All right, so we're missing one element in this here. That's good fun. So as we're sorting this, we seem to have ended up with one element that got stranded at the end. Oh, no, I'm sorry. We just never printed our array at the end. That's good, because I did not want to debug that right now. We always good to make sure you know what you're printing. We're just missing the last set of swaps, I think. So now this should be sorted. All right, that's good. So the general pattern, as you can see, is our index is increasing. And as our index is increasing, we are doing these swaps to get a value back to where it's supposed to be. So take a look at what happens at index 10. The array looks like this so far. It's sorted, and now we're looking at this 400 that's at the end. Then you can watch this 400 be swapped all the way back down until it ends up right next to a value that it belongs next to, and then we exit our loop. And you can see that same kind of neat diagonal pattern inside each of these as you see through. See the 740? 740 then ends up bubbling down to where it's supposed to be and ends up there. Or if we look at, looking at index 8, this 19 is not where it's supposed to be. So we find this 19 and we say, hey, while 19 isn't where it's supposed to be, and it's not at the beginning, keep on swapping. And we end up swapping that back down. I wonder why our 80, yeah. We do one more swap on printing this. I should print this at the end, shouldn't I? All right, fine. So we do all that swapping down until we end up with our element where our element is supposed to be. So in this one, we've got a 329 that ends up swapping down until it ends up such that it's bigger than the number right to the left of it. So this is our in-place insertion sort done via these nested loops structure. And so we see that it's still not a very efficient algorithm to sort with. If I give it 10,000 things, which is not a crazy amount of posts that you might want to load at one time in an app that you're building. We're even printing, good Lord. So we're doing all kind of, wow, that is going really slowly. Our print statements are making this take a while. it will run on this for quite some number of times before it's content with itself. Let's see if we froze it or not. Because in general, the order of magnitude that it's going to take is relative to the square of the original thing that we had. Now, it's going to be less than that because, like, we know as a matter of practicality, if we end up here and swap, like, we can only look at the things to the left of us. We're not going to look at the things to the right of us. So at the beginning, it's not our second while loop isn't going to take that much time. But at the end, it takes a lot of time to end up going through. Do I still have a print statement in there? Wow, this is really slow. So you can see how slowly these grow, right? Is like, because you can watch in real time, like looking at the 82nd thing, the 83rd thing, the 84th thing, the 85th thing. That's taking a really long time in between cycles, right? To sort 10,000 things here and just print out what it's doing might take minutes, which is a truly unacceptable amount of time to be sorting something in the context of an application on your phone. You would not wait minutes for a sort button to work on any application you use, right? So this is an algorithm that's good to know because the work that a lot of people did later was, hey, this isn't very efficient. Maybe there's a way to make it faster. There was a time before, not a time that was actually useful for computing things, but a time mathematically where this was the most efficient algorithm people had come up with. And then someone had to come up with a way of sorting that was better. So for now, these are our two sorts that we have, which are very slow and inefficient, but insertion sort and bubble sort are two sorts that you'll hear people talk about a lot as they crop up in CS programs who just talk about what is a basic algorithm like that takes in some inputs, gives you some outputs. So that's what insertion sort looks like. Questions on what we've seen so far? It's only like 3 lines, right? That'd be simple. Oh, that's fun. That's because I'm spending all my processor speed trying to sort something. We're saved. Right now? No, it just takes forever. Look, yeah, we're counting up to 10,000, and that's how slow it's counting. That's a really long time. So I'm really trying to drive home that quadratic algorithms are really inefficient, right? You should know how they work, but you should be very wary in an interview-like problem. It's rare that the best solution for something is going to be in quadratic time. Might happen, but it's not very good. Yeah. Any question? So the only time we're making a range is inside this line right here, right? So to make sure that as you're making your range, yeah, I kind of wish it would let you do that, but it doesn't. But yeah, make sure that you have, if you're making ranges explicitly, that your left number is less than your right number. I'll slack this all out in characters. If you do need to reverse a range, their dot reverse will give you a reverse range, and you can actually iterate through it backwards. Kind of cool. They can do for like for index in like 0 dot dot less than r dot count. Put that in parentheses dot reversed. Index will start at the top of the array and then go down. Yeah. So if you had a set, sets can't be ordered, right? There's no way to have any type of order inside of the set because, and we talked about a little of that with hash maps. The way that sets are built is a collection of, remember this, a hashing algorithm and an underlying array. And a set is a special thing that doesn't have any order that it remembers. It can't tell you what went into it at what time, but it can tell you very quickly if something's there or not. So you will not see a sort on the built-in set or dictionary for that matter inside of Swift, because it doesn't make sense conceptually to be sorting a set. Because there's no order to a set anyways. Yeah. But sets are a really useful thing in algorithm problems to know, primarily because they're very efficient at getting elements that are sorted This is really slow, isn't it? Look how slow that is. That's very slow. It's going to take a long time. Mainly because our array has so many elements in it here. Yeah. It's very human. Yeah, exactly. I think especially the one we did first where you just build an array and then you sort it there. Like, if you just gave me a deck of cards and told me to sort it, we would not bubble sort it. What I would do is I would look through and I'd find an ace and I'd just put it in a pile. And then I'd look through and find a 2 and then put it in a pile. And I'd keep doing that like over and over until it's sorted. So insertion sort is really like a first stab kind of approach, especially the not in place. That's why I like it as an algorithm, because like you said, it's a very human kind of algorithm. The one, even the in-place one is much less human. Bubbling is a little bit weird, but still kind of makes sense. Like just shift backwards until you find where it's supposed to go. It's kind of a clever thing you could do with a deck of cards, it's a little tricky. The ones we'll see next are absolutely not things you'd ever do as a reasonable person. They're very clever, but they're just not things that like make sense as a person to organize. Because they're better than this, and they're linear rhythmic, it means they do weird things with cutting things in half a lot. So like the way to be sorting a deck of cards the faster way is like take a deck of cards and cut it. Then take each of the cuts and then cut those, and then keep cutting them. And then keep cutting them until you end up with 52 cards that are all next to each other. And then you take each of those 2 pairs and you put those in order. And then you take each of those 2 things and you put those in order, and you keep repeating that. It's really weird. It's really fun. We'll look at that next week. In terms of practice with this here, if you look on Canvas, if I haven't irredeemably broken my computer, there should be a link, maybe if you're lucky, even with a submission link on it. We'll see. And that should have the lab link for you. The lab is pretty much the same as the bubble sort lab, except you should use insertion sort. It also has test stuff built into it. You are not 6'2". You are largely 6'1". And it's great. So the insertion sort stuff, great. Has the same type of stuff, build the same type of problems, has the same little tricky bit where you have to worry about ignoring zeros, and the tricky bit where you got to build something to work with a linked list. So use this as another opportunity first to just like look at the like 2 of the questions are things that are in the lesson that'll slide. Just like make sure you know what's going on with them. Do it on paper. Like really, like if you're looking at that while loop and you're like, I still don't really know what this is doing, write out an array like this on paper, and then just like go through and say, here's the value of index 1, here's the value of index 2. I'm going to go ahead and say, is this while condition true? I'm going to figure out if it's true or not, and then I'm going to go through it. And it really helps like that with more complicated algorithms to do it out with like pencil and paper. Okay. Any other questions? Yes? Which one? Oh, this here? Yeah, this is a closure. The type of the closure says, you give me 2 of the same thing, and I tell you true or false. In this here, it says, you give me 2 things, and I tell you if they're sorted. So you give me like 2 and 5, and I say, is it true that 2 and 5 are sorted? So when we're calling this, as we do here, this is the closure. It's a little bit trimmed down. This is short form for something like $0 is less than $1 inside of a closure syntax here. So this is our closure. It's saying, I'm giving you an array of integers and a rule that says 2 integers are sorted if the first one is smaller than the second one. It's a way of giving the user an additional way of specifying what it means for something to be sorted. And that's the same thing that Swift does, which is why I built it into this here. You could just always sort things small to greatest. They get a little bit of bonus points if, like, during an algorithm, like interview kind of thing, you know conceptually that this is something available in Swift, and you know how you might write something like it. Yeah. And that is represented by like having that tuple first type here, but the whole type of this is this. This is a type. Just like int is a type, just like string is a type, parens t returns bool is a type. It's It's a closure. It's a function that takes in two numbers and returns two generic t things, whatever they could be. Could be numbers, could be strings, could be whatever. They just have to give us a rule for how to sort them. Cool. All right, I will leave you then to starting the lab stuff. Let me know if you have any other questions on it, and I will go ahead and work more on uploading video stuff and then Slack this out. Let me do that right now. Lechkamor, go and study. Here's one. All right, so I've Slacked that out to you as well, and I will also Slack out the lab link just for good measure. Thank you. I've got to run to a meeting, but you'll see me around.